Welcome back to This Explainer. Today, we're picking right up with part 2 of our deep dive into vapor pressure, and we're zeroing in on this single absolute threshold that dictates the entire gas carrier industry.
Let's kick things off with a super quick thermodynamics refresher.
So, as we covered in part 1, temperature and pressure, they are permanently locked together on the saturation curve. It's a fundamental physical law. As you heat a sealed cargo, its internal vapor pressure automatically rises along that specific curve. You really can't get around it. And remember, every one of those curves eventually hits a hard limit, right? The critical temperature. That's the absolute ceiling where a substance can no longer exist as a liquid, no matter how much pressure you apply. For methane, that hits at minus 82.6 degrees Celsius. Above that exact point, physics takes over, and it is physically incapable of staying liquid. All right, with the physics locked in, let's move on to the legal gatekeeper. You see, the IMO IGC Code doesn't mess around with arbitrary definitions or vague descriptions. It relies on one strict thermodynamic boundary to act as the legal gatekeeper. Literally, one single number decides if your cargo is legally a gas cargo or not. And here is that magic number, 2.8 bar absolute at 37.8 degrees Celsius. Seriously, burn this number into your memory. Under the IGC code, if a liquid's vapor pressure crosses that 2.8 bar line at that specific temperature, you are no longer shipping it on a standard tanker. You suddenly require purpose-built gas carrier compliance. Now, you might be wondering, why 37.8 degrees Celsius? Well, it's not just a random poll. This is the standardized reference temperature chosen specifically to represent the absolute worst-case ambient heat of a tropical day. Cross that 2.8 bar line in those conditions, and you absolutely need a purpose-built, pressure-rated containment system. Let's put some real vapor pressure numbers on this to see how it plays out in the real world. Think about propane. At 37.8 degrees, its vapor pressure is sitting at roughly 13 bar absolute. I mean, that is miles over the threshold, definitively an IGC cargo. But then consider something like ethylene oxide. It sits just underneath at 2.7 bar. It's incredibly close, but legally, because it doesn't cross the threshold, it flows right into the regular tanker category. So, this 2.8 bar line marks the exact point where a standard chemical tanker structure can no longer safely contain the thermodynamic pressure buildup. A standard chemical sits comfortably under 1 bar. Propane pushes close to 13. Which brings us to the severe danger of cargo mislabeling. This is exactly why substitution errors or bad paperwork are so incredibly dangerous. If a cargo's actual vapor pressure turns out to be higher than what the paperwork claims, maybe because of a contaminated mix or a mislabeled batch, you are effectively pumping IGC threshold pressure into a standard hull. And on a hot day, a hull that wasn't designed for it could literally crack under the strain. It's why verifying actual vapor pressure before loading is never just a paperwork formality. It's the vital operational reality check that keeps your vessel safely on the correct side of the regulatory line. Okay, let's do a quick test of the rule to make sure this is all clicking. Imagine this scenario. Your cargo reads 1.5 bar absolute at 37.8 degrees Celsius. Does it legally require an IGC-compliant gas carrier? Think about it for a second. Nope, because 1.5 bar falls well below the 2.8 bar threshold, standard tanker classification applies. It's a really great reminder that just because a cargo is quote-unquote liquefied, that does not automatically mean it's IGC regulated. Let's pull this all together and look at the complete thermodynamic chain. Before, maybe boiling points and vapor pressures were just disconnected facts you had to memorize. But now, you can trace the entire chain. Temperature and pressure walk hand in hand up the saturation curve. They hit that critical temperature ceiling, and ultimately that 2.8 bar threshold is the legal line that dictates the exact ship type required. It is the physics underneath every single cargo you'll ever load. Of course, understanding these physical rules is what keeps the cargo safely contained. Next time, we're going to cover what happens when it isn't. We'll be diving into the intense safety and handling chemistry of toxic and reactive cargoes, and the specific failure modes that have actually killed people on ammonia carriers, like carbamate blockages. But for now, I want to leave you with this. If that single 2.8 bar line is literally all that stands between safe containment and a shattered hull on a blazing hot tropical day, are you absolutely certain of the true vapor pressure inside your tanks right now? Thanks for joining me for this explainer, and I'll see you in the next one.